There is an aircraft flying right now that you will never see. Not because it is far away, though it is. Not because it is small, though some of them are. But because it was designed from the very first line drawn on the very first page of its engineering specification to be invisible. Its shape was calculated not for beauty and not for speed, but for the specific purpose of returning no useful signal to a radar receiver on the ground. It moves through the upper atmosphere in complete silence from the perspective of anyone below. A machine worth hundreds of millions of dollars, built by thousands of engineers over decades of work, crossing the sky without a trace. Most of us never think about what is above us at night. The sky looks empty. It is not empty. Welcome to simple science. If these slow, careful explorations of the world's hidden machines help you find rest at the end of a long day, please like this video and subscribe to the channel. New stories arrive every single day, and we would love for you to be here for them. Before we begin, leave a comment below and tell us where you are watching from and what time it is there. We genuinely read every one. Now, let us go up. Military aviation occupies a strange place in the imagination. When most people think of military aircraft, they think of speed and noise, of afterburners and low passes, and the kind of sound that rattles windows from a mile away. Those things exist, but they are not the whole picture, and they are not what this story is about. This story is about the other side of it, the drawing boards and the test ranges, and the long, silent cruise legs at altitude where a single pilot sits inside a canopy of reinforced glass and watches the curve of the Earth from a height where almost nothing else lives. The sky at 40,000 feet is a different world from the one we occupy on the surface. The temperature outside the aircraft's skin is around -57 degrees Celsius. The air pressure is roughly 1/5 of what it is at sea level. The sky above is a deeper, richer blue than anything visible from the ground, shading toward indigo at the zenith, where the atmosphere thins enough that the black of space begins to show through at its edges. Below, the weather moves in slow, enormous patterns. Storm systems the size of countries rotating, with a kind of patient authority that makes the surface world look very small and very temporary. A pilot cruising at that altitude is not thinking about combat. They are not thinking about the aircraft's weapons, or its radar, or its electronic warfare systems. In a long transit leg, with the aircraft trimmed and stable, and the autopilot holding altitude and heading, the pilot's mind settles into something that experienced aviators consistently describe in similar terms. A particular quality of attention, wide and present without being anxious. The awareness of someone responsible for something that requires their full care, but in a moment when that care is not being tested. It is, in its own way, one of the most meditative working environments in the world. The machines that enable this experience took over a century to develop. They began as wood and canvas contraptions that could barely clear a fence. They became, through engineering of extraordinary ambition and patience, vehicles capable of traveling faster than the speed of sound, of flying above the effective ceiling of the atmosphere, of carrying out missions in complete darkness without a single visible light. Every step of that development involved thousands of quiet hours of calculation, of testing, of refinement, of people sitting at desks and at drawing boards and in wind tunnels, working through problems that had never been solved before, because the machines that posed them had never existed before. Tonight, we are going to spend some time with those machines, not with their weapons, not with their wars, but with their engineering and their physics and the world they inhabit when everything is going right and the sky is clear and the only sound inside the cockpit is the steady, low note of turbines doing what they were built to do. The sky has always had secrets. Tonight, some of them belong to you. In the winter of 1903, on a beach at Kitty Hawk, North Carolina, a bicycle mechanic from Dayton, Ohio, flew a powered aircraft for the first time in human history. The flight lasted 12 seconds. The aircraft covered 37 meters. Orville Wright was lying on his stomach on the lower wing, controlling the aircraft by shifting a cradle with his hips that warped the wing surfaces, a technique he and his brother Wilbur had developed over years of careful observation of birds. There were 5 witnesses. One of them took a photograph. 8 years later, in 1911, the Italian military dropped bombs from an aircraft over Ottoman-held Libya. It was the first time in history that a heavier-than-air machine had been used as a weapon. The aircraft was a Farman biplane, a fragile arrangement of wood and wire and fabric that flew at about 60 kilometers per hour and could barely carry the weight of its pilot and the small grenades he dropped by hand over the side. The Wright brothers had been flying for less than a decade. The military had already found a use. The speed of that transition says something about the century that followed. The aeroplane was barely invented before it became a weapon, and barely a weapon before it became a sophisticated one. The First World War, which began in 1914, accelerated the development of military aviation in the way that war always accelerates engineering, by creating an urgent, well-funded need for something that performs better than what the enemy has. At the start of the war, military aircraft were used primarily for reconnaissance. A pilot would fly over enemy positions and report what he saw. They were unarmed. The early assumption on all sides was that aircraft were observation platforms, nothing more. That assumption did not survive the first year of the war. Pilots began carrying rifles and pistols into the air to shoot at enemy reconnaissance planes. Then, machine guns were fitted to the aircraft. Then, the problem of firing a machine gun through a propeller arc without destroying the propeller needed to be solved, and Dutch aircraft designer Anthony Fokker solved it in 1915 with a synchronized gear system that timed the gun's firing to the gaps between the spinning propeller blades. Within 2 years of that invention, dedicated fighter aircraft existed, single-seat machines built specifically to shoot down other aircraft, with names like the Fokker Eindecker, the Sopwith Camel, and the Spad S-13. The pilots who flew them became the first generation of fighter pilots, and some of them became the first aviation heroes. Their names reported in newspapers, and their kill counts tracked the way sports statistics are tracked. The Red Baron, Manfred von Richthofen, flew a red-painted Fokker triplane and was credited with 80 aerial victories before he was shot down and killed in April 1918 at the age of 25. By the end of the First World War, aircraft had been built that could drop significant bomb loads on targets far behind the front lines. The Handley-Page 605/1500, a British heavy bomber designed to reach Berlin from English airfields, had a wingspan of 38 meters and could carry 30 bombs of 113 kilograms each. The war ended before it flew a combat mission. But the aircraft existed, and the fact that it existed told anyone paying attention that the age of strategic bombing had arrived, and that the sky would never be a neutral space again. All of it, every sophisticated military aircraft that came after, from the Spitfire to the B-52 to the F-35, traces its lineage back to that fragile Farman biplane over Libya in 1911. And behind that, to 12 seconds on a cold morning on a North Carolina beach. And behind that, to two brothers who looked at birds and decided that the way they tilted their wings to turn was the answer to a problem no one had yet solved. The fact that a wing generates lift is one of the most well-established facts in physics. It is also, if you spend enough time with it, one of the most quietly astonishing. Consider what is actually happening. A piece of metal shaped in a specific curve is moving through air. The air, encountering the front edge of the wing, divides. Some goes over the top surface, some under the bottom. Because of the wing's curved upper surface, the air travelling over the top has a longer path to travel than the air going under. To cover that longer path in the same time, the air over the top must move faster. Faster moving air exerts less pressure on the surface it passes over. This is the Bernoulli principle, described by the Swiss mathematician Daniel Bernoulli in 1738, 165 years before the Wright brothers used it to leave the ground. So the air above the wing is moving faster and pressing down less than the air below. The higher pressure below pushes up. The lower pressure above pulls up. The result is lift, an upward force generated purely by the shape of the wing and the speed at which it moves through the air. That is the simplified version, and it is largely accurate. The fuller picture also involves the angle of attack, which is the angle between the wing's chord line, an imaginary straight line from the leading edge to the trailing edge, and the oncoming airflow. A wing tilted slightly upward into the airflow generates more lift by deflecting air downward, and the equal and opposite reaction pushes the wing up. Fighter pilots use angle of attack constantly, pitching the nose up to generate more lift in tight turns, trading airspeed for the increased force needed to change direction quickly. Every military aircraft ever built is, at its most fundamental level, a wing management system. Everything else, the engine, the weapons, the electronics, the fuel, the pilot, exists to support the function of the wing, to keep it moving through air at the right speed and the right angle to generate the lift required to keep the aircraft aloft. When that function fails, everything else fails with it. The wings of different military aircraft look very different from each other because they are optimized for different tasks. A long-range strategic bomber like the B-52 Stratofortress has long, straight wings that are extraordinarily efficient at generating lift at moderate speeds over very long distances. A fighter like the F-16 has a delta-shaped wing, a roughly triangular form that performs well at supersonic speeds and in high-G maneuvers. The A-10 Thunderbolt II, a ground attack aircraft built to fly slowly and survive damage, has straight wings with a thick profile that generates lots of lift at low airspeeds. Each shape is a specific answer to a specific set of requirements, the product of thousands of hours of calculation and wind tunnel testing and aerodynamic compromise. The wing of a modern military aircraft is not a simple metal sheet. It contains fuel tanks embedded within the wing structure and holding hundreds or thousands of liters of aviation fuel that shifts as the aircraft maneuvers. It contains the mechanisms that extend and retract the flaps and slats, the movable surfaces on the leading and trailing edges that change the wing shape for takeoff and landing. It contains sensors and wiring. On stealth aircraft, it contains radar-absorbing material embedded in its skin, and it contains, if you were to look at a cross-section under a microscope, the accumulated knowledge of every aeronautical engineer who worked on wings from Bernoulli in 1738 to the present day. Every test flight and every calculation and every failure that was learned from and corrected and built upon. A wing is a slow idea that took a very long time to arrive at and then changed everything. In 1972, a small group of engineers at General Dynamics in Fort Worth, Texas, began working on an idea that went directly against most of what the United States Air Force believed a fighter aircraft should be. The prevailing doctrine at the time held that air superiority fighters should be large, fast, complex, and expensive. The aircraft that embodied this doctrine was the F-15 Eagle, which was then in development, a twin-engine, 18-ton aircraft capable of Mach 2.5 and loaded with the most advanced avionics available. It was a magnificent machine by any measure. It was also extraordinarily costly, which meant that fewer of them could be built, which meant that any attrition in combat would quickly reduce the available fleet. The engineer who challenged this thinking most forcefully was a man named John Boyd, a former fighter pilot and Air Force officer who had developed a theory of aerial combat that emphasized energy management over raw speed. Boyd argued, based on his analysis of air combat in the Korean War, that the ability to change speed and direction faster than an opponent was more important than any other performance characteristic. What the Air Force needed, he believed, was a small, light, highly agile fighter that could outmaneuver any opponent at close range. He called his concept the lightweight fighter. The program that emerged from Boyd's advocacy was a design competition between General Dynamics and Northrop, resulting in the YF-16 and the YF-17 prototypes. The YF-16 first flew on February 2nd, 1974, in an unscheduled first flight. Test pilot Phil Ustricher was conducting a high-speed taxi run along the runway when the aircraft began to roll uncontrollably due to the extreme sensitivity of its fly-by-wire control system. Faced with the choice of allowing the aircraft to depart the runway and suffer a ground accident or pulling it into the air, he flew it. The official first flight happened a few weeks later, on January the 20th, 1974. But the accidental one is the one most aviation historians remember. The YF-16 won the competition and became the F-16 Fighting Falcon, which entered service with the USAF in 1978 and has since been operated by 25 countries with more than 4,600 aircraft built. It was everything Boyd's theory predicted. Light, agile, extraordinarily maneuverable, and powered by a single engine that gave it a thrust-to-weight ratio greater than 1, meaning it could accelerate vertically in a straight climb. An aircraft that weighs less than the force pushing it forward is, in the most literal sense, defying gravity not just with its wings, but with its engine. The process that produced the F-16, from the first theoretical papers Boyd wrote in the late 1950s to the aircraft entering operational service, took roughly 20 years. That timeline is not unusual for a major military aircraft program. The F-22 Raptor took from its initial advanced tactical fighter requirement in 1981 to operational service in 2005, a span of 24 years. The F-35 Lightning II program began with a Joint Strike Fighter requirement in 1996 and delivered its first operational aircraft in 2015. These timelines exist because the problems being solved are genuinely hard. An operational military aircraft must fly reliably for decades, in temperatures ranging from Arctic cold to desert heat, maintained by mechanics in field conditions far from a factory, carrying systems of extraordinary complexity, and it must perform at the edge of what physics allows without exceeding it. Getting that right takes time. It takes failure. It takes the slow accumulation of knowledge that only comes from building the thing, flying it, finding what breaks and fixing it over and over until the aircraft that emerges from the process is ready for the sky. Close the canopy. The outside world goes quiet, not silent, because the aircraft is running and the engines are producing a low, steady note that travels through the airframe into the seat beneath you. But the wind, the ambient noise of the flight line, the voices of the ground crew, all of that disappears when the canopy locks. What is left is the cockpit, and the cockpit is a world of its own. A modern military cockpit is among the most information-dense small rooms ever designed. In the F-35 Lightning II, the aircraft currently in frontline service with the US military and more than a dozen allied nations, the pilot wears a helmet that costs approximately $400,000. That helmet contains a display system that projects flight information, targeting data, and sensor feeds directly onto the visor, so the pilot can read their airspeed and heading and threat information without looking away from whatever they are looking at. Cameras mounted around the aircraft's fuselage feed imagery to the helmet so that the pilot can, in effect, look through the floor of the aircraft by looking down inside the cockpit. The aircraft becomes transparent. Beneath the helmet, the ejection seat is the most important piece of equipment in the cockpit that the pilot hopes never to use. The Martin Baker ejection seat, fitted to many Western military aircraft, can take a pilot from zero airspeed at zero altitude, meaning sitting on a runway, to safely under a parachute in under 2 seconds. It fires using a rocket motor that generates forces of up to 20 times the force of gravity on the pilot's spine during the ejection sequence. The seat is designed to operate at airspeeds up to around 900 kilometers per hour and at altitudes from the ground to above 15,000 meters. It saves lives routinely. Martin Baker estimates that its seats have saved more than 7,600 lives since the company began producing them in 1944. In front of the pilot, the instrument panel in a modern fighter is dominated by 1 or 2 large multifunction displays, flat screens that can be configured to show whatever information is currently most relevant. The primary flight instruments, altitude, airspeed, attitude, are typically displayed on a dedicated screen or on the heads-up display projected onto the inside of the canopy. The heads-up display, or HUD, projects key flight data as a transparent overlay on the pilot's forward view, so they can read their speed and altitude while looking directly at the horizon. In older aircraft, before digital displays became standard, the instrument panel was covered in individual dials, each one measuring a single parameter. A pilot learning to fly a 1960s Aerojet fighter learned to scan those dials in a specific sequence, building a mental picture of the aircraft's state from dozens of separate readings taken in rapid succession. The transition to glass cockpits as the multifunction display error is called, reduce the number of individual instruments, but increase the density of information available on each screen. The pilot's job shifted from scanning many simple displays to managing fewer but more complex ones. The throttle and control stick in a modern fighter carry numerous buttons and switches, allowing the pilot to change display modes, control weapon systems, and manage the radio without removing their hands from the primary controls. This is called HOTAS, which stands for hands-on throttle and stick. The design principle is that in a high-stress maneuvering engagement, the pilot's hands cannot leave the controls to reach for switches on the panel. Every function that might be needed in that scenario is therefore accessible from the throttle or the stick. The oxygen system feeds through a hose from the seat to the mask on the pilot's face. Above 10,000 feet, supplemental oxygen is required for sustained mental performance. Above 40,000 feet, the outside air is so thin that even pure oxygen at ambient pressure is not enough, and the system pressurizes the oxygen flow slightly. Pilots flying at very high altitudes wear pressure suits that partially compensate for the reduced atmospheric pressure outside the aircraft. In normal cruise flight, at a comfortable altitude with the aircraft trimmed and stable, none of this complexity demands the pilot's active attention. The systems run. The displays show normal parameters. The aircraft holds its heading and altitude. The pilot watches the sky, and the instruments in the practiced, easy scan of someone who has done this many hundreds of times. Alert without effort, present without strain. Outside the canopy, the sky is whatever the sky is today. This is the part that no amount of engineering fully describes. The physical world, visible through the glass, above the clouds and below the stars. On the morning of May 15th, 1941, a Gloucester E-28/39 aircraft lifted off from RAF Cranwell in Lincolnshire, England, powered by an engine that contained no pistons, no crankshaft, and no propeller. It flew for 17 minutes and reached a top speed of 545 kilometers per hour. The engine was a Whittle W1 turbojet, designed by Royal Air Force officer Frank Whittle, who had first patented the concept of the jet engine in 1930, and spent the following decade fighting the British aviation establishment for the resources to build one. Whittle was 23 when he filed that patent. He was a scholarship student at the RAF College Cranwell, the son of a mechanic, and he had been thinking about high-speed flight since he was old enough to understand that propeller-driven aircraft had a fundamental speed limit. A propeller generates thrust by pushing air backward, but as the aircraft goes faster, the tips of the propeller blades begin to approach the speed of sound, generating shock waves and losing efficiency rapidly. For aircraft to fly faster, a different kind of engine was needed. Whittle's solution was elegant. Instead of using a piston engine to drive a propeller, he would use the energy in burning fuel to create a continuous flow of high-pressure, high-temperature gas that would exit the engine at speed and push the aircraft forward by reaction. Air enters the front of the engine, is compressed by a series of rotating blades, mixed with fuel and ignited in a combustion chamber, and the resulting high-energy gas stream is expelled through the rear of the engine via a turbine. The turbine extracts enough energy from the exhaust to drive the compressor at the front, and the rest of the energy becomes thrust. This is the turbojet in its basic form. It is the principle on which every jet engine built since has operated. In Germany, Hans von Ohain had reached the same fundamental insight independently, and had the advantage of working for an aircraft manufacturer, Ernst Heinkel, who gave him the resources Whittle spent years trying to obtain from the British government. The Heinkel, a 178, powered by von Ohain's Hochsess 3 engine, flew on August 27, 1939, 2 years before Whittle's aircraft, making it the first jet-powered aircraft to fly. Von Ohain and Whittle met after the war and became friends. Two men who had solved the same problem from opposite sides of a conflict that neither of them had chosen. The engines that power modern military aircraft are turbofans, a development of the basic turbojet that dramatically improves fuel efficiency. A turbofan has a large fan at the front that moves air through two separate paths. Some goes through the core of the engine and is burned with fuel to generate thrust, and a larger amount bypasses the core entirely and is accelerated through the engine casing to produce thrust at lower temperature and velocity. The ratio of bypass air to core air is called the bypass ratio. High bypass turbofans, the kind used in commercial airliners, have bypass ratios of around 10:1 or higher and are very fuel efficient, but cannot achieve supersonic flight. Low bypass turbofans, used in military aircraft, sacrifice some fuel efficiency for the ability to reach supersonic speeds. The General Electric F110 engine, which powers many variants of the F-16 and F-15, produces roughly 76,000 newtons of thrust without afterburner and approximately 129,000 newtons with afterburner engaged. Afterburner works by injecting additional fuel into the hot exhaust stream behind the turbine and igniting it, adding a substantial amount of thrust for a large cost in fuel consumption. It is used for short bursts, for takeoff on short runways, for initial climb, and for supersonic acceleration. The characteristic long flame visible behind a fighter aircraft taking off at night is the afterburner's visible output, a controlled jet of burning fuel extending several meters behind the aircraft. The engines of a modern fighter aircraft have a service life measured in thousands of hours between major overhauls and in tens of thousands of hours of total operation. They operate at temperatures inside the combustion chamber that exceed the melting point of the turbine blades themselves, which survive only because of cooling systems that flow air through microscopic channels inside each blade. The blades are single crystal castings, grown in a furnace from a single seed crystal, so that there are no grain boundaries in the metal that could become failure points under thermal stress. They are extraordinary objects, these engines. Products of 7 decades of incremental refinement of an idea that a young RAF officer wrote down in a patent application in 1930, working in a rented workshop with inadequate funding and the skepticism of an establishment that could not yet see what he already understood. The B-2 Spirit bomber first flew on July 17, 1989, from Air Force Plant 42 in Palmdale, California. The test pilot was Bruce Hines, and his co-pilot was Colonel Richard Couch of the United States Air Force. The aircraft that lifted from the runway that morning was unlike anything that had ever flown. It had no fuselage in any conventional sense. It had no vertical tail surfaces at all. It was, essentially, a single wing, a perfect flying wing 52 meters from tip to tip, its surface broken only by the gentle humps of the 2 engine bays and the subtle lines of the crew compartment canopy blended into the leading edge. Seen from certain angles, it disappeared almost entirely against the sky. The B-2 is the most expensive aircraft ever built, at roughly $2.1 billion per aircraft, when total program costs are divided across the 21 aircraft produced. It is operated exclusively by the 509th Bomb Wing at Whiteman Air Force Base in Missouri. It can carry either conventional or nuclear weapons, fly without refueling from Whiteman to any target on Earth and back, and deliver that payload with extraordinary precision. And it can do all of this while appearing on radar as an object approximately the size of a large bird. Stealth technology is not a single invention. It is the combination of two distinct approaches to reducing an aircraft's radar signature: shaping and materials. Shaping works by controlling the angles at which the aircraft's surfaces reflect radar energy. A conventional aircraft has many curved surfaces and angled edges that scatter radar energy in multiple directions, some of which returns to the receiver and reveals the aircraft's presence. A stealth aircraft uses flat panels arranged at specific angles that reflect radar energy away from the receiver rather than back toward it. The F-117 Nighthawk, the first operational stealth aircraft, was built from flat facets, giving it an angular, almost crystalline appearance that made it look like something from a science fiction film. The B-2 achieved the same result through a different approach, using smooth curves derived from specific mathematical equations that produced a surface that continuously deflected radar energy away from any transmitter direction. Materials work by absorbing rather than reflecting radar energy. Radar-absorbing material, known as RAM, is typically a composite that contains carbon or iron particles in a matrix designed to convert incoming radar energy into heat rather than reflecting it. The exact composition of the RAM used on operational stealth aircraft is classified, but the basic principle has been publicly documented since the 1970s. RAM is applied to the surfaces of stealth aircraft as a coating, and maintaining it is one of the most demanding aspects of keeping a stealth aircraft operational. Each B-2 requires hundreds of hours of maintenance on its RAM coating between missions, work that must be done in climate-controlled facilities because the material's performance is sensitive to temperature and humidity. The result of all this engineering is an aircraft that is, in a very specific technical sense, hidden, not invisible to every detection method. Modern radar technology, particularly low-frequency radar, can detect even well-designed stealth aircraft at certain ranges. But the stealth aircraft's signature is reduced sufficiently that it can approach defended targets before those defenses can effectively respond. There is a quality to the B-2 that people who have seen one in person consistently remark on. It is not a fighter's aggressive beauty, all sharp edges and visible power. It is something quieter than that. It sits on its landing gear with a strange, settled stillness. The wings so wide and flat that it seems more like a geographic feature than a machine, more like a plateau than a vehicle. Its engines are buried deep inside the wing, their intakes shaped and positioned to prevent radar from directly illuminating the compressor faces. Its exhaust exits through slots at the trailing edge, designed to mix hot exhaust with cool air before it exits the aircraft and reduce the thermal signature visible to infrared sensors. It is a machine that wants to be nothing, and in pursuit of that, it became something genuinely unlike anything else in the sky. On the morning of October 14th, 1947, Charles Elwood Yeager, a 24-year-old Air Force captain from Hamlin, West Virginia, climbed into a Bell X-1 rocket-powered aircraft that had been slung under the belly of a B-29 bomber at 20,000 feet over the Mojave Desert in California. He did this with 2 broken ribs. 2 days earlier, Yeager had been riding a horse at a ranch outside Muroc Army Airfield when the horse threw him. He hit a fence rail and cracked 2 ribs on his right side. He went to a doctor in the nearby town of Rosamond, rather than the base doctor, because the base doctor would have grounded him. He was told the ribs were cracked, not broken, and that flying was possible, though uncomfortable. He did not tell the Air Force. He told only his close friend and fellow test pilot Jack Ridley, who helped him devise a workaround for the fact that his injuries made it impossible to seal the cockpit door, which required him to reach across his body and pull a handle with his right arm. Ridley cut a piece of broomstick and showed Yeager how to use it as a lever to close the door one-handed. That morning, the B-29 climbed to 20,000 feet and released the X-1. Yeager ignited the rocket engine, pulled up, and began the run toward Mach 1. At approximately Mach 0.88, the aircraft began to buffet, a severe shaking caused by shock waves forming on the wing surfaces. At previous attempts, the buffeting had been bad enough to make the controls ineffective. This time, Yeager deployed the all-moving horizontal tail, a feature of the X-1 that allowed the entire tail surface to pivot, rather than just a hinged elevator. The buffeting stopped. The aircraft accelerated through the transonic zone. At approximately 10:26 in the morning, the machmeter in the X-1 jumped off its scale. The aircraft had gone supersonic. At Mach 1.06, traveling at approximately 1,127 kilometers per hour at an altitude of 13,000 meters, Yeager became the first human being confirmed to have flown faster than sound. The sound of this event, the sonic boom, arrived at the desert below some seconds after the aircraft had already passed the speed of sound. The people on the ground heard a crack, a sharp double report that rolled across the Mojave. Yeager described the moment of transition as surprisingly smooth. The violent buffeting disappeared. The aircraft flew cleanly. He had been told that the sound barrier was a physical wall, that the aircraft would break apart going through it. On the other side of it, there was nothing but clear, fast air. Yeager's story became famous eventually, largely through Tom Wolfe's 1979 book, The Right Stuff. But he was not the only test pilot doing work of equivalent courage and significance during that era. At the same base, on the same desert, in the years that followed, men were flying aircraft that had never been in the sky, aircraft built from theoretical designs that might be exactly right, or might fail catastrophically, with no way to know until someone was in it. The culture of flight testing operated on a specific understanding of risk. These pilots were not reckless. They were systematic. They approached each flight as an experiment, defining what they intended to test, what parameters they would stay within, what the abort criteria were. The courage was not the absence of fear, but the presence of preparation, detailed enough that fear could be managed rationally. Yeager was not brave because he ignored the risk of the broken ribs. He was brave because he assessed the risk, concluded it was acceptable, and made a specific practical plan to manage it. There is a generation of test pilots, most of them now gone, who flew things that had no business being in the air and found out whether the engineering was right by being there when it mattered. The aircraft we fly now, military and civilian, carry their work in every component. The world below has gone dark. The aircraft departed the base at 2200, shortly after sunset, and has been climbing for the last 20 minutes through a layer of scattered cloud that thinned and then disappeared somewhere around 20,000 feet. Above the cloud, the sky is clear and the stars are out, but the pilot is not looking at them. The pilot is looking at the cockpit displays, which present the world in two forms: the flight instruments showing the aircraft's state, and the FLIR display showing the terrain below as a thermal image. FLIR stands for Forward-Looking Infrared. It is a sensor system that detects heat rather than light, converting temperature differences in the scene below into a video image where warm objects appear. Bright and cool objects appear dark, or in some display configurations, the other way around. On the FLIR display, a road appears as a grey ribbon slightly warmer than the surrounding fields. A river appears as a dark line slightly cooler. A building appears bright because it has been absorbing heat all day and is releasing it slowly into the cooler night air. A vehicle engine glows with the heat of combustion. Night vision goggles, fitted to the pilot's helmet and looking through the cockpit canopy, amplify the available light by factors of several thousand, turning a dark landscape with only starlight and the faint glow of distant towns into a green-lit scene detailed enough to navigate by. Flying with night vision goggles at low altitude is one of the most demanding tasks in military aviation. The field of view is narrowed compared to normal vision, depth perception is reduced, and the goggles shift the pilot's apparent center of vision slightly, requiring specific training to compensate. Military helicopter pilots, in particular, spend extensive hours mastering the technique. The first wide-scale use of night vision equipment in combat aviation was during Operation Just Cause in Panama in 1989, and during Operation Desert Storm in 1991, where the ability to operate freely at night gave coalition aircraft a significant advantage over Iraqi forces that lacked equivalent technology. Night had been the natural protector of ground forces for all of military history. After 1991, that protection was substantially reduced for any force fighting against a technologically advanced opponent. But night flight, when nothing is happening and the mission is simply a transit across dark terrain from one place to another, has a quality that day flight does not. The world below has retreated. Its detail is hidden, visible only in thermal impressions and the occasional cluster of lights from a town or a highway. The sky above is clear and full of stars that are somewhat more visible at altitude than they are on the ground, because less atmosphere stands between the aircraft and them. The cockpit environment at night defaults to a particular low-light mode. Instrument panels are dimmed, the heads-up display brightness is reduced. The red advisory lights, if they illuminate, are set at lower intensity, so they do not compromise the pilot's night-adjusted vision. The overall effect is a cockpit that glows very softly, all its instruments visible but none of them bright. The outside darkness pressing against the canopy. Pilots who fly extensively at night describe a specific kind of focus that the darkness creates. The visual world is simplified, reduced to what the instruments and the sensors show. The cognitive load of the full visual scene, the roads and fields and buildings and weather that a daylight flight presents, is replaced by a more abstract, symbol-based representation. In some ways, it is easier to think clearly. The world has been reduced to its essential information, and the task of flying the aircraft through it is correspondingly cleaner. Outside the canopy, the dark world moves slowly below. The aircraft is high enough that its own lights, if it were showing any, would be visible for miles in any direction. It is showing none. It moves through the dark as the dark does, without announcing itself, leaving nothing behind. Before October 1947, the sound barrier was not a metaphor. It was a widely held hypothesis based on real experimental data that described a physical limit beyond which aircraft could not fly. The data supporting this view was not wrong. Aircraft attempting to approach the speed of sound in the early 1940s encountered phenomena that were genuinely violent and genuinely dangerous. As an aircraft's speed approaches Mach 1, approximately 1,235 kilometers per hour at sea level, air begins to compress in front of the leading edges faster than it can flow away. Shockwaves form on the wings and fuselage, regions of rapidly changing pressure that create turbulence severe enough to make control surfaces ineffective. Early jet aircraft entering a dive and inadvertently approaching transonic speeds experienced what pilots described as compressibility, a sudden and alarming loss of control authority, where the stick moved and the aircraft did not respond as expected. Several pilots died in accidents that were attributed to compressibility effects in the mid-1940s. The data from these accidents, combined with wind tunnel results that showed drag increasing enormously as Mach 1 was approached, led some aerodynamicists to conclude that the sound barrier was indeed a barrier, that the energy required to exceed it was greater than any practical engine could produce, and that the structural stresses would destroy any aircraft that got close enough. They were wrong, but their error was understandable. The wind tunnels of the early 1940s were themselves inadequate for transonic research, because the shock waves that formed at the tunnel walls at near sonic speeds corrupted the data. The aerodynamicists were working with measurements that were physically misleading. The solution to the wall of drag that accumulated at transonic speeds was discovered independently by two aerodynamicists, Adolf Bussmann in Germany, who proposed swept-wing aircraft in 1935, and Richard Whitcomb at the NACA Langley Research Center in Virginia, who formulated the area rule in 1952. Bussmann's swept wing delayed the formation of shock waves by changing the effective angle at which air met the leading edge. Whitcomb's area rule described how the cross-sectional area of an aircraft should vary smoothly along its length to minimize wave drag. The Convair F-102 Delta Dagger was redesigned using Whitcomb's area rule, its fuselage given a distinctive pinched waist like a bottle, and in this form it exceeded Mach 1 in level flight for the first time in 1954, where the original design had been incapable of doing so. Yeager's flight in the X-1 had proved that the barrier was a feature of the aircraft, not a fundamental limit of nature. The right aircraft, built for the specific conditions of transonic flight, could go through it and find the other side. What it found on the other side was, in Yeager's own description, and in the description of every pilot who followed, surprisingly peaceful. The buffeting stopped. The aircraft flew smoothly. The controls became effective again. Supersonic flight, above the wave drag zone of the transonic regime, was in many ways easier than the turbulent approach to it. When an aircraft exceeds the speed of sound, it outruns the pressure waves its own passage creates. Sound travels at the speed of sound. An aircraft going faster than that is always ahead of its own acoustic signature. The pressure waves pile up behind and around the aircraft in a cone of compressed air, and where that cone intersects the ground, observers hear a sonic boom. The double crack that represents the simultaneous arrival of the shockwave from the nose and the shockwave from the tail of the supersonic aircraft. From inside the aircraft, the transition produces no sound at all. The pilot does not hear the sonic boom because the boom is falling behind. What they hear is whatever the cockpit was already producing: the engine note, the airflow, the radio, and, if the instruments are being read correctly and the aircraft is behaving well, nothing that calls for alarm. The sky above Mach 1 is the same sky as the sky below it. The aircraft passes through a number and the world continues. Somewhere far below and far behind, the boom arrives at the desert floor, and the people standing there know that something just went through a place where the air was not large enough to contain it. Somewhere over the North Atlantic, at 30,000 feet, two aircraft are flying in formation so close that the distance between them is measured in meters. The aircraft in front is a Boeing KC-135 Stratotanker, a large four-engine jet that carries up to 90,000 kilograms of aviation fuel in tanks distributed through its wings and fuselage. Behind it, slightly below and slightly to the right, is a fighter aircraft closing the gap with a patience and precision that its pilot has practiced hundreds of times in training, and that still, every single time, requires the full weight of their concentration. The fighter is moving forward at around 500 kilometers per hour. The tanker is moving forward at the same speed. The relative velocity between them is nearly zero. They are, in effect, two metal objects hanging in the air next to each other, while both travel at the speed of a bullet. Aerial refueling was first successfully demonstrated in 1923, when two US Army Air Service aircraft passed a fuel hose between them while both were flying. The pilots managed to complete the transfer after several failed attempts, and the technique that seemed like a stunt in 1923 became one of the defining capabilities of modern air power by the second half of the 20th century. Without aerial refueling, every military aircraft in the world is limited by its internal fuel capacity. With it, range becomes a function of how many tankers are available, and an aircraft that could otherwise fly for 4 hours can stay airborne for 12 or more. The United States Air Force uses the boom system, developed in the 1940s and refined continuously since. A telescoping rigid boom extends from the tail of the tanker, operated by a boom operator who lies prone in the rear of the aircraft, looking through a window at the receiver aircraft approaching from behind. The receiver flies into a specific contact envelope, a box of airspace defined by the tanker's flight characteristics and the boom's reach, and holds position there. The boom operator extends the boom and makes contact with a receptacle on the top of the receiver aircraft's fuselage. A valve opens, fuel flows. The boom operator is not a pilot. They are an enlisted or warrant officer specialist, trained specifically for this task. And in the community of people who understand aerial refueling, they are regarded with considerable respect. The workload during a contact is high. The boom operator is flying the boom with a small joystick, maintaining the connection while both aircraft move slightly, relative to each other in the turbulence that is always present at altitude. If the receiver moves too far outside the envelope, the boom disconnects automatically, a breakaway that both aircraft are trained to handle. NATO allies and many other nations use the probe and drogue system rather than the boom. In this system, the tanker trails a flexible hose from a pod under its wing, and a basket or drogue is fitted to the end of the hose to stabilize it. The receiver aircraft has a fixed or retractable probe, extending from its nose or fuselage, and the pilot flies that probe into the basket to make contact. This requires the pilot to be looking slightly upward and forward at a basket that is moving in the tanker's wake, and to fly the probe into a target roughly 60 centimeters in diameter, while both aircraft are traveling at several hundred kilometers per hour, and the basket is oscillating slightly in the disturbed air. The first few contacts in a pilot's training are described universally as humbling. The basket moves in a way that looks predictable from outside the aircraft, but feels chaotic from inside it, because every small correction the pilot makes changes the airflow around the nose and shifts the basket's position in response. The technique is to fly the aircraft, not chase the basket, to hold a stable position slightly back from the basket and let it oscillate into the probe rather than trying to follow it. It takes time to learn. Once learned, it is the kind of skill that, like riding a bicycle, does not entirely leave. The moment of contact, when the probe seats in the basket and the valve opens and the fuel begins to flow, is confirmed by a green light in the cockpit and a slight change in the sound of the airflow around the probe. The pilot holds position. The fuel flows. At 1,500 litres per minute, a typical transfer takes between 5 and 15 minutes. Then, the pilot disconnects, eases back from the tanker's wake, and the full fuel load that went in is already being burned at the front of the flight envelope for everything that comes next. The flight deck of an aircraft carrier is approximately 333 meters long and 77 meters wide on a Nimitz-class carrier, one of the largest warships ever built. At any given moment during flight operations, that space contains aircraft being launched, aircraft landing, aircraft being refueled and rearmed, and the people managing all of it in a choreography so precisely timed and so visually complex that first-time observers consistently describe it as the most organized chaos they have ever seen. It is not chaos. Every person on the flight deck has a specific role, identified by the color of their jersey. Yellow jerseys direct aircraft on deck. Blue jerseys move aircraft and operate the elevators that bring them up from the hangar deck below. Red jerseys handle weapons and crash and salvage. Green jerseys handle catapults and arresting gear and aircraft maintenance. Purple jerseys, called grapes, handle fuel. White jerseys are for safety observers, landing signal officers, and quality assurance. The color system allows any new arrival on the deck to immediately identify who does what, in an environment too loud for voice communication to be the primary coordination tool. The catapult system used on American carriers is one of the engineering marvels of modern military infrastructure, made less visible by the fact that it operates mostly below the deck surface. The C-13-2 steam catapult, which was the standard system on Nimitz-class carriers before the newer electromagnetic catapult entered service, uses high-pressure steam stored in accumulators below the deck and released in a controlled burst to drive a shuttle along a track in the deck. The shuttle connects to the aircraft's nose wheel, and the steam drives it from 0 to flying speed in roughly 2 seconds across a deck run of about 100 meters. The forces involved accelerate the aircraft at roughly 3 times the force of gravity. The pilot and crew brace for it, and it is over before the mind fully registers that it happened. Landing on a carrier is considered by most naval aviators to be the most demanding routine task in military flying. The aircraft approaches from behind the ship, following a glide path indicated by a system of lights on the deck edge, called the Fresnel lens or ball, which gives the pilot a visual reference for whether they are high or low on the approach. The target landing area is a strip of deck behind the arresting wires. 4 cables stretched across the deck that the aircraft's tailhook catches on touchdown. If the hook catches a wire, the aircraft decelerates from about 240 kilometers per hour to 0 in approximately 2 seconds. A deceleration of roughly 4 times the force of gravity. If the hook misses all 4 wires, the aircraft must go around for another attempt, which is why pilots are trained to push the throttle to full power the moment the wheels touch the deck, rather than pulling back, so that a bolter, a missed wire, results in the aircraft flying off the angle rather than running off the end. The angled deck, a British innovation introduced in the early 1950s, made this possible. Before the angled deck, carrier flight decks were straight, which meant that a missed landing resulted in the aircraft colliding with the aircraft parked at the bow. The angled deck, offset about 9 degrees from the ship's centerline, provides a clear runway for approaches that allows bolters to fly off the side of the ship without endangering the aircraft parked forward. It is one of those design solutions that seems obvious in retrospect and was not obvious at all until someone thought of it. The landing signal officers, 2 of them, stand at the aft end of the angle on a small platform extending beyond the deck edge. They watch every approach, grade every landing, and maintain radio communication with every inbound pilot. Their job is to tell the pilot when the approach looks right, and to wave them off when it does not. The wave-off is mandatory. A pilot who ignores a wave-off faces serious consequences, because the landing signal officers can see things from outside the aircraft that the pilot cannot perceive from inside. And their judgment about whether a particular approach is recoverable is the last check in the system. The carrier at night, during night flight operations, is a different world from the day. The flight deck is lit only by the minimum necessary lighting, a pattern of dim lights marking the deck edges and the centerline. The aircraft approach with their own lights on, visible from miles away as they set up in the landing pattern. And the sea around the ship is dark in all directions, an enormous flat darkness broken only by the ship itself, its wake, and the pale moving lights of the aircraft coming in from the night. On July 4th, 1956, a black aircraft took off from an airfield in Wiesbaden, West Germany, and flew east across the border into the Soviet Union. It flew at 70,000 feet, which its designers were confident was above the service ceiling of any Soviet interceptor. It photographed military facilities across a wide swath of the Western Soviet Union and returned safely. The Soviet military detected it, tracked it, and could not reach it. Premier Nikita Khrushchev lodged a furious protest with the Eisenhower administration 4 days later. The aircraft was the Lockheed U-2, designed by a team led by Kelly Johnson at the Lockheed Skunk Works facility in Burbank, California, and built in secret under a program codenamed Aquatone. Johnson was the most gifted aircraft designer of his generation, a man whose basic approach to engineering was to reduce everything to its essential function and eliminate everything else. The U-2 was the embodiment of that philosophy. It was built to fly very high and carry cameras. Everything about it was optimized for those two functions. It had enormous glider-like wings that could generate lift at the thin air of extreme altitude. It had a single engine, the minimum required. It had no weapons, no defensive systems, no armor. It weighed as little as Johnson's team could make it weigh, because at 70,000 feet, every kilogram of unnecessary weight was a kilometer of ceiling given up. The U-2 is still in service with the United States Air Force today, more than 60 years after its first flight. Updated versions carry sensors that were unimaginable in 1955. But the basic airframe is recognizably the same aircraft Kelly Johnson designed. It remains one of the most efficient high-altitude aircraft ever built. The SR-71 Blackbird came later, and it represented the opposite end of the speed spectrum from the U-2. Where the U-2 survived by going high and slow, the SR-71 survived by going high and extremely fast. It was designed to cruise at Mach 3.2, approximately 3,900 kilometers per hour, at altitudes around 85,000 feet. At that speed and altitude, no missile or interceptor of its era could catch it. If a surface-to-air missile was fired at it, the SR-71's response was to accelerate. The engineering challenges of building an aircraft to cruise at Mach 3.2 were significant in ways that had no precedent. At that speed, air friction heats the aircraft's skin to temperatures that would destroy conventional aluminum alloys. The SR-71 was built primarily from titanium, a material far more resistant to heat but far more difficult to machine and weld. The production process for its titanium structure required new tools, new techniques, and new skills that Lockheed's manufacturing teams had to develop specifically for this aircraft. The fuel used in the SR-71, designated JP-7, was a specially formulated kerosene blend with a very high flash point, meaning it required a deliberate ignition source to burn and would not ignite from heat alone, despite the extreme temperatures on the airframe. The aircraft's fuel system was designed to deliberately leak slightly on the ground because the titanium structure expanded significantly at operating temperature and only sealed fully in flight. The SR-71 holds speed records that remain unbroken. On September 1st, 1974, an SR-71 flew from New York to London in 1 hour, 54 minutes and 56 seconds, at an average speed of 2,908 kilometers per hour. On July 28, 1976, an SR-71 set the absolute airspeed record for a jet aircraft at 3,529.56 kilometers per hour, a record that still stands. From 85,000 feet, the curvature of the Earth is visible. The sky above the SR-71's canopy was not blue. It was the dark, rich purple-black of the upper atmosphere, the boundary where air ends and space begins. The horizon was not a line, but a curve, the gentle arc of a planet seen from high enough to understand its shape. Below, the weather moved in continent-scale patterns, and the ground was textured and slow and impossibly distant. The pilots who flew the SR-71 described the view from that altitude the same way consistently. The word most of them reached for, eventually, was perspective. The F-22 Raptor is the most capable air superiority fighter currently in service with any air force in the world. It can supercruise, meaning it can maintain supersonic flight without using afterburner. It is nearly invisible to radar. It can maneuver at angles that would be aerodynamically impossible without its fly-by-wire control system, which the aircraft's computers manage in fractions of a second faster than any pilot could react. It is, by the consensus of the people who study these things, the most advanced combat aircraft ever built. It also requires approximately 30 hours of maintenance for every 1 hour it spends in the air. That ratio, 30:1, is not a failure of engineering. It is the predictable consequence of building an aircraft to the absolute edge of what is technically possible with current materials and manufacturing methods. The F-22's stealth coating is precise and sensitive. The low observable materials on its surfaces require careful inspection after every flight and repair when needed. Its systems are complex enough that diagnosing and correcting faults requires specialized training and equipment. The aircraft is, in a meaningful sense, a precision instrument that happens to fly, and precision instruments require meticulous maintenance. The people who do this work are called crew chiefs, and each aircraft has a dedicated crew chief who is, in the culture of military aviation, personally responsible for that aircraft's condition. The relationship between a crew chief and their aircraft is one of the closer professional relationships in the military world, in part because the stakes of its failure are so high, and in part because the aircraft becomes, over time, familiar in the way that any complex machine becomes familiar to the person who tends it daily. A crew chief knows their aircraft's history. They know which fasteners have been replaced and when, which systems have been written up and corrected, which panels have been opened, and how many times. They know the sounds of the aircraft starting, the smell of its hydraulic fluid, the particular way its APU, the auxiliary power unit, catches on a cold morning versus a warm one. This knowledge is partly in the technical logs and partly in the crew chief's memory, and the two together constitute a picture of the aircraft's condition that no maintenance record alone can fully capture. Before every flight, the crew chief conducts a pre-flight inspection of the aircraft, walking through a checklist that covers every surface, every panel, every visible component that could affect airworthiness. The pilot also conducts a pre-flight walk-around, but the crew chief's inspection is more thorough, more detailed, and reflects a deeper familiarity with that specific aircraft. When the pilot climbs in, the crew chief assists with the strapping in process, helps with the oxygen connections, and stands at the front of the aircraft as the engine starts, watching the engine intake area until the intake temperature is confirmed safe, then stepping clear. When the aircraft launches, the crew chief watches it go. There is a specific way that experienced crew chiefs watch a launch, a stillness and attention that is distinct from the casual watching of a bystander. They are watching for anything that is not right, anything that should not be there in the exhaust pattern, or the gear retraction sequence, or the climb profile. Most of the time, everything is right. The aircraft climbs away clean and disappears into the sky. The crew chief turns back to the line, and the work of preparing for recovery begins. When the aircraft returns and shuts down, the crew chief is there again, There is a particular satisfaction in the working relationship of a crew chief and an aircraft that comes from having sent something into a demanding environment and received it back intact. The maintenance logbook is updated. The next pre-flight is scheduled. The aircraft is serviced and secured. The flight hours are the visible part of military aviation. The maintenance hours are the invisible part, the larger part, the part without which the visible part cannot happen. The mechanics who keep military aircraft flying are, in the most literal sense, the reason the aircraft fly at all. On a clear morning over the Nevada desert, 6 aircraft are turning through a wide banking turn in a formation so tight that the distance between any 2 wingtips is less than 2 meters. They are moving at 700 kilometers per hour. They have been flying together for 20 minutes, and in that time, no aircraft has been more than a meter from its assigned position. From the ground, they look like a single large aircraft banking through the morning light. From inside any one of the cockpits, the view is an adjacent aircraft, close enough that the rivets in its skin are clearly visible. Formation flying is one of the oldest disciplines in military aviation. The first tactical fighter formations were developed during the First World War, when pilots discovered that flying alone was significantly more dangerous than flying in coordinated pairs or groups, because a pilot focused on attacking a target was vulnerable to another enemy aircraft attacking from behind. The British and German air services developed different solutions to this problem, and out of those solutions grew the concept of the mutual support formation, in which each aircraft covers the vulnerable areas behind its partner. The Luftwaffe pilot Werner Mulders, who flew in the Spanish Civil War in the 1930s, refined the German approach into what became known as the Rotte, a pair of aircraft, and the Schwarm, a group of 4 arranged in a loose finger 4 formation. This formation, which positioned 4 aircraft at the corners of a widely spaced diamond when viewed from above, gave each pilot good visibility and allowed mutual coverage without requiring the tight proximity of earlier parade-style formations. The RAF adopted a similar concept after encountering the Schwarm in the Battle of Britain, abandoning the tight Vic formations they had been using, which looked impressive but provided poor mutual support in combat. The aerodynamic benefits of formation flying were understood qualitatively for decades before they were fully analysed. The leading aircraft in a formation produces a pressure field around it as it moves through the air, and following aircraft flying in the right position within that pressure field experience reduced aerodynamic drag. This is the same principle by which birds fly in V formations. Canada geese flying in V formation consume roughly 20 to 30% less energy than they would flying solo, according to research published by Henri Weimerskirch and colleagues at the Centre d'études biologiques de Chizé in France in 2001. Military aircraft flying in the right echelon position behind a leader benefit from similar drag reductions, translating directly into fuel savings on long-range transit flights. The precision aerobatic display teams that exist in several air forces, including the Blue Angels of the United States Navy, the Red Arrows of the Royal Air Force, and the Frecce Tricolori of the Italian Air Force, take formation flying to an extreme that serves no operational combat purpose. The Blue Angels fly their diamond formation, 4 aircraft in an arrowhead, with approximately 1.2 meters of separation between aircraft at show speeds. The pilots maintain position not by looking at their instruments, but by selecting specific visual reference points on the adjacent aircraft and holding those references constant. A Blue Angel pilot in the diamond formation is holding a point on the leader's cockpit frame perfectly still in their forward vision, while both aircraft travel at 600 kilometers per hour. The training pipeline for a Blue Angel's pilot takes a full season before a new pilot joins the show schedule, and the physical and mental demands of maintaining that precision for a full display are significant. After a show, the debrief is recorded and every frame of the flight is reviewed. Any deviation from the standard is noted, discussed, and corrected before the next performance. These teams exist because human beings find controlled precision beautiful, not because it has a military utility beyond demonstrating that the aircraft can be flown this way, not because it communicates a threat, but because watching 6 aircraft move through the sky as if they share a single nervous system produces a response in the viewer that is difficult to describe and not difficult to feel. The beauty of something done exactly right, in a medium as unforgiving as the air, by people who have given years to the discipline of doing it. The engine note changes slightly on the climb, not enough to generate an alert, not enough to change any reading on the instruments, but enough that the pilot registers it, a half-tone shift in the low-frequency background of the cockpit, and files it away at the back of their attention for the rest of the flight. That is what training in a complex aircraft eventually produces, not just the ability to read instruments, which any attentive person can learn relatively quickly, but the ability to hear the aircraft and know from its sound what it is doing and how well. The sound of a correctly functioning jet engine at cruise is a continuous, multi-layered note with specific components. The high whine of the compressor, the lower frequency rumble of combustion, the airflow over the canopy. Together, they form a signature that the pilot learns over hundreds of hours, until departures from it register without conscious analysis. The cockpit of a modern military aircraft is not quiet. It cannot be quiet, because it is surrounded by machinery and enclosed in a thin metal shell, travelling through dense air at high speed. The noise level requires hearing protection, and pilots wear specialised headsets that cover the ear canal, and simultaneously reduce ambient noise and deliver radio communications. The radio is the most constant voice in the cockpit on any mission, a stream of calls between aircraft in the flight, between the flight and air traffic control, between the flight and the mission coordinator, and on-guard frequency, a specific channel monitored by all aircraft where emergency calls and urgent traffic are broadcast. On a long transit leg with no active tasks, the radio goes quiet for minutes at a time. The mission controller might check in every 20 minutes for a position report. The wingman might make a routine fuel check call. Between those calls, the only sound is the cockpit, the engine, the airflow, the soft hiss of the oxygen system, the occasional chime of a navigational waypoint as the aircraft crosses it. Experienced pilots describe this quiet differently, depending on their temperament. Some find it uncomfortable, particularly early in a career, because the absence of active task work leaves the mind with nothing to do, and it looks for problems. Some find it peaceful in a way that is qualitatively different from other forms of peace, because the responsibility of being in command of a complex aircraft at altitude is present and real, but when everything is working correctly, that responsibility requires only a light, steady attention, rather than active effort. The mind rests in a vigilant calm that is not available in most other environments. This quality of attention is sometimes described by pilots as being in the aircraft rather than flying it. The distinction they are drawing is between the state of a student pilot who is consciously processing each input and output and managing each task with deliberate effort, and the state of an experienced pilot who has integrated the aircraft's behavior into their own sensorimotor system to the degree that minor corrections happen below the level of conscious thought. Flying has become, in a specific sense, natural. The aircraft is an extension of the body that flies it. The silence inside a cockpit means something. A pilot who has been flying for a long time knows from the cockpit's acoustic signature whether the aircraft is normal. They know the sound of a hydraulic pump cycling, the sound of the landing gear doors sealing, the sound of the fuel boost pumps at low tank levels. These sounds are not dramatic. They are part of the background, the constant, low, alive hum of a machine doing its job, carrying a person through airspace that nobody else in the world is occupying at this moment, above weather that is real, and below stars that are closer than they are from the ground. Somewhere in that continuous sound, if you have been sitting in enough cockpits for long enough, there is something that quiets the part of the mind that will not settle anywhere else. Above 40,000 feet, the world below has simplified itself into something almost abstract. The ground is there, visible on a clear day as a pattern of textures and colours that correspond loosely to what a map shows. Brown desert, dark mountain ranges, the silver threads of rivers catching the sunlight at oblique angles, the white geometry of salt flats. Occasionally, if the light is right, the grid of a city, regular and pale against the surrounding landscape, spreading out from a centre like the rings of a slow impact. Weather, which dominates the experience of the surface world and shapes the experience of flight at lower altitudes, has mostly fallen away. At 40,000 feet, the aircraft is above the tops of all but the largest convective storms, the thunderstorms that build in the afternoon heat of summer and reach their anvil tops into the lower stratosphere. Those storms are visible from this altitude as white cauliflower columns rising from a lower layer of cloud, their tops flattening where they hit the tropopause, the boundary between the troposphere where weather lives and the stratosphere above it. They look slow from up here. They are not slow. Inside one of those columns, wind speeds can exceed 150 kilometers per hour, and updrafts can tear an aircraft apart. From above, they look like sculpture. The sky at cruise altitude is a color that has no common name. It is blue, but not the blue of a clear sky seen from the ground, which is a product of the full depth of the atmosphere, scattering sunlight in all directions and filling the dome of the sky with diffuse light. At 40,000 feet, the depth of atmosphere above the aircraft is much smaller, and the sky directly overhead begins to shift into a deeper, darker register, a blue that is closer to indigo, at the very top of the troposphere, edging toward the dark of the upper atmosphere, where the scattering thins and space begins to show through. The SR-71, operating at 85,000 feet, was above 95% of the Earth's atmosphere. At that altitude, the sky overhead was the blackish violet that precedes full darkness in space. The boundary between the sky and space is not a line. It is a gradient that the human eye experiences as a color shift, and the pilots who flew at that altitude consistently described the overhead sky as something that did not match any color they had seen from the ground. The SR-71's pilots could see the curvature of the Earth from the horizon. At 85,000 feet, the horizon is approximately 1,000 kilometers away in any direction, and the arc of that distance across the surface of a sphere 12,742 kilometers in diameter is clearly visible as a gentle bow of the horizon line. The planet is round in a way that is intellectually understood from childhood and experientially confirmed only from a height that almost no human being reaches. Below the cruising altitude of a modern fighter in the 30,000 to 40,000 foot range, the view is less extreme but no less wide. The sun at that altitude is a sharper, brighter disk than it appears from the surface, because less atmosphere stands between the aircraft and it. Shadows are harder edged. Colors are more saturated. The light has a clarity that photographers and painters who have studied high-altitude photography consistently remark on as different from anything available below the weather layer. And there is the silence. Not silence inside the cockpit, which is never truly quiet, but the silence of the outside world, as experienced from inside it. The aircraft is traveling at 900 kilometers per hour. The mountain range below is enormous and ancient and indifferent. The weather is a layer of white far below. The planet is doing what it has always done, turning through its day. The pilot is somewhere above all of it, briefly, in a machine that took a century of human effort to build, looking at a view that very few people will ever see, in a quiet that is available nowhere else. Davis-Monthan Air Force Base sits in the Sonoran Desert, southeast of Tucson, Arizona, at an elevation of about 800 meters, in a region that receives less than 30 centimeters of rain per year. The air is dry. The soil is hard caliche, a concrete-like layer of calcium carbonate that lies just below the surface across much of the Sonoran Desert, and is firm enough to support the weight of heavy aircraft without paving. The combination of low humidity, hard ground, and more than 350 days of sunshine per year makes this particular patch of desert the ideal place to park aircraft you might want again someday. The 309th Aerospace Maintenance and Regeneration Group, known universally as the AMARG and less formally as the Boneyard, has been operating at Davis-Monthan since 1946. It currently stores more than 4,000 aircraft of approximately 80 different types. They are arranged in rows, organized by type, across an area of approximately 11 square kilometers. Seen from the air, the Boneyard looks like the world's largest parking lot, except that what is parked there includes B-52 Stratofortresses, F-14 Tomcats, A-10 Thunderbolts, C-130 Hercules transports, and dozens of other types in various stages of preservation or disassembly. Aircraft arrive at the Boneyard by flying in from their last operational base, or by being towed in if they are no longer airworthy. On arrival, they go through a preservation process called cocooning, in which a white vinyl butyrate compound called spraylat is applied to all windows, openings, and bare metal surfaces to protect them from ultraviolet radiation and the slight but not zero moisture in the desert air. Aircraft in long-term storage have their engines sealed, their landing gear, oleos nitrogen purged, their fuel tanks drained and treated. Preserved this way, an aircraft can sit in the desert for decades and remain in a condition from which it can be returned to flight-ready status with manageable effort. The reason this matters is that a significant number of the aircraft stored at Davis-Monthan are not there permanently. They are there as a strategic reserve, an insurance policy against a future conflict that requires more aircraft than the active fleet can provide. During the Vietnam War, aircraft were pulled from desert storage and returned to service. During Desert Storm, spare parts from Boneyard aircraft supported the deployed fleet extensively. The stored aircraft are not relics. They are resources, held in reserve, the way any prudent organization holds resources it might need. Some aircraft at the Boneyard are designated for parts reclamation, rather than possible return to service. These are systematically disassembled, their serviceable components removed, and entered into the supply system to extend the service lives of active aircraft. The rest goes to the smelter. A B-52, which weighs about 83,000 kilograms empty, contains enough aluminum, steel, and titanium to make that disassembly economically significant. And some aircraft sit in the desert in a category that is genuinely ambiguous. Too old to return to frontline service, too historically significant to destroy, not yet formally preserved. They sit in their rows with their spraylat peeling in the desert sun, their markings fading, their cockpits empty and hot. They flew for decades, maintained and fueled and armed and repaired by thousands of people whose names are not recorded anywhere in the aircraft's history. They carried those people's work into the sky every time they flew. In the late afternoon, when the desert light goes amber and the shadows of the aircraft stretch long across the Kalichi, the rows at Davis-Monthan have a quality that is hard to name precisely. It is not sad, though it could be read that way. It is closer to the quality of things that are finished, that have done what they were built to do, and are resting now in the dry air of the desert, still here, still whole, in the particular quiet of machines that no longer have anywhere to be. On October 4th, 1957, the Soviet Union launched Sputnik 1, the first artificial satellite, into low Earth orbit. It was about the size of a beach ball, weighed 83 kilograms, and transmitted a radio signal on 20 and 40 megahertz that amateur radio operators around the world could receive. It completed an orbit of the Earth every 96 minutes. The United States government, which had been watching the Soviet missile program with concern, received the news of Sputnik with an urgency that accelerated the development of what became the modern space program, the internet, and the satellite navigation systems that are now embedded in every smartphone. The connection to military aviation is direct. The technologies that produced the missiles and launch vehicles of the late 1950s and 1960s grew from the same engineering ecosystem as military aircraft development. The same companies, many of the same engineers, the same government funding structures, and the same urgent need to develop things that had never existed before. The US Defense Advanced Research Projects Agency, DARPA, was established in 1958 directly in response to Sputnik, with a mandate to ensure that the United States would not again be surprised by a foreign technological development. DARPA funded the research that produced the ARPANET, the precursor network to the Internet, beginning in 1969. GPS, the Global Positioning System, began as a US Department of Defense program called NavStar, authorized in 1973 and achieving initial operational capability in 1993. Its original purpose was to provide precise navigation for military forces, aircraft, ships, and missiles, reducing the dependence on ground-based navigation aids that could be jammed or destroyed. The system was made available to civilian users free of charge in the 1980s, initially with a deliberate degradation of accuracy called selective availability that was switched off in 2000 by executive order. Today, GPS receivers are in phones, cars, shipping containers, and agricultural equipment. The system processes approximately 1 billion location requests per day. It began as a military aviation navigation tool. Weather radar, now used in every commercial airliner and in the weather forecasting systems that supply the daily forecasts on every phone, developed from the radar systems installed in military aircraft in the 1940s and 1950s to allow all-weather navigation and to detect airborne threats. The technology that allows a passenger on a commercial flight to track the weather systems the aircraft is routing around was developed to give fighter pilots the ability to find targets in cloud. The pressurized aircraft cabin, which allows passengers on commercial flights to breathe normally at 35,000 feet without supplemental oxygen, was developed for military aircraft in the late 1930s and early 1940s. The Boeing 307 Stratoliner, a commercial airliner that first flew in 1938, had a pressurized cabin derived from the Boeing B-17 bomber then in development. Without pressurization, commercial aviation as it exists today would be impossible. Passengers could not fly above the weather layer, and aircraft could not achieve the fuel efficiency of high-altitude cruise, and global air travel would be slower, rougher, and far more expensive. The Ray-Ban Aviator sunglasses, designed in 1936 for US Army Air Corps pilots by optical engineer John McCready Jr. and manufactured by Bausch and Lomb, became one of the most widely sold sunglasses in the world, worn by people who have never been in an aircraft and never will be, because the lens shape and frame design that worked for a pilot in an open cockpit in 1936 also happens to look right on a human face. The microwave oven came from a Raytheon engineer named Percy Spencer, who was working on radar magnetrons in 1945 and noticed that a chocolate bar in his pocket had melted during a test. Spencer experimented with popcorn and then with an egg, which exploded, and filed a patent for a cooking device using microwave radiation the same year. The first commercial microwave oven, introduced in 1947, stood 1.8 meters tall and weighed 340 kilograms. All of it, the navigation, the communication, the food that cooks itself, the sunglasses, the weather that is no longer a surprise because you can see it on a screen, came from the same long, patient, expensive effort to build aircraft that could do what no aircraft had done before. The last aircraft has landed. The flight line is quiet now. The aircraft lined up on the ramp in the dark with their covers fitted and their wheels chocked, and the ground crew gone home for the night. The desert air has cooled from the day's heat. The stars are out in the specific abundance that the desert sky produces, far from any city, far from any light. Above all of this, the sky is empty. It is not always empty. During the day, and often at night, it contains aircraft, military and civilian, crossing the country at various altitudes on their various missions. But at this hour, in this particular corner of airspace, there is nothing up there. The air is just air, moving slowly in the high altitude winds that always blow. circulating around the planet in the jet streams and the trade winds and the polar flows that have been moving since long before any aircraft existed to fly through them. The sky holds no record of what has passed through it. An aircraft can fly at 40,000 feet, leave a contrail that dissipates in minutes, and within an hour there is no trace of it. The air closes behind every flight the way water closes behind a ship, without hesitation, without memory. The sound of every engine that has ever run, every sonic boom from every aircraft that has broken the sound barrier, every radio call on every frequency, has radiated outward from its source and dispersed into the universe without being stored or retained in any recoverable form. This is one of the quieter facts about the sky. It does not accumulate. It is always, in some fundamental sense, new. The aircraft on the ramp have their own accumulated history, recorded in logbooks and maintenance records, and the memories of the people who maintained them. But the sky they flew through is clean and open and identical to the sky that existed before any of them were built. The same air that carried Frank Whittle's first jet aircraft in 1941 has long since dispersed and recirculated. The same sky that Chuck Yeager crossed faster than sound in 1947 is the same sky that is above you right now, wherever you are, in whatever season. There is something genuinely restful about this. The sky is so large, and the history of what has happened in it is so rich and strange and human, and all of it has passed through without leaving a mark on the sky itself. The sky absorbed it and closed over it and kept going. Tonight it is above you, doing what it has always done. The jet stream is blowing at whatever speed it blows tonight, somewhere above 30,000 feet. The stars are there, in the positions that always make them findable. The temperature at the top of the troposphere is whatever it is, cold and stable, as it always is at that altitude. Up there, a long way above where you are, the air thins into the indigo of the upper atmosphere, and above that into the black of space. And somewhere in that black, the stars that the SR-71's pilots could see from 85,000 feet are doing what they have done for billions of years before tonight, and will continue to do long after it. You are here, down below the weather, down below the clouds if there are any, down at the surface where the air is thick and breathable and warm, where the aircraft are parked and quiet, and the flight line is dark, and the desert has gone still. The sky tonight asks nothing of you. The aircraft are taken care of. The mechanics finished their work hours ago. The pilots are home. The engineers who designed every component of every aircraft that ever flew through this airspace did their work years before any of us were paying attention. And it is done, and it is good, and the sky holds all of it lightly, the way the sky holds everything. You have been up there with the pilots and the mechanics and the engineers tonight, in the only way that matters, which is in the imagination that makes distant things present and complex things legible, and the vast, cold sky above you into something worth knowing. You can come back down now. The sky will still be there. If these quiet journeys into the world's extraordinary machines give you something to rest in at the end of your day, please like this video and subscribe to Simple Science. We are here every single day with a new world to step inside, something true and worth knowing before you sleep. And if you made it all the way here, through every cockpit and every altitude and every engine room we visited tonight, leave us a comment. Tell us where you are watching from and what time it is. we will be thinking of you wherever the sky is above you tonight.